Now we are going to determine the internal resistance of a cell. For that we are going to consider the same condition as usual for the potentiometer. First, initially let us assume that we have a cell of internal EMF epsilon 1 and internal resistance of small r, and for that we are getting the equation as VAC1, that is equals to epsilon 1, and that is also equals to sigma L1. Now if we are going to consider that we are connecting one external resistance capital R parallel to this condition, we are going to have the null point at a point C2, and for that VAC2 is going to be V, that is equals to sigma L2. But according to Ohm's law, we have previously that V is equals to epsilon minus I r only. So from that equation we can see that epsilon 1 is equals to V plus IR, and here according to Ohm's law V is going to be IR only. So IR plus small IR, and that's why epsilon 1 is equals to I capital R plus small r. Now we are going to divide both these equations, that is epsilon 1 upon capital V. So epsilon 1 upon capital V, according to these equations, epsilon 1 is equals to sigma L1 and V is equals to sigma L2. So epsilon 1 by V is equals to L1 by L2, but V is equals to IR, so epsilon 1 upon IR, that is equals to L1 by L2. Putting out the values of epsilon 1, I small r in the bracket small r plus capital R upon IR, I cancel, small r plus capital R upon R, that is equals to L1 by L2. If we are simplifying this equation, we are getting the value that small r is equals to capital R L1 by L2 minus 1, and small r is the internal resistance of the battery of EMF epsilon 1 only. So these are the practical applications for the potentiometer.